seen, called a magnetic monopole. We've all seen a magnet. There it is. It's got a north pole and a south pole, and we all played with those. The idea is that there would be a special kind of particle that only has one pole. We can't imagine that. Every magnet we've ever seen has a north pole and a south pole, and you can hook them together. This is called a magnetic monopole. Where are they? We've never seen one. People have been looking for a long time. We'll explain all three of these. So now, before we get into understanding what Alan Guth's model of inflation does, we have to refresh on the concept of maps. So here's a map. This happens to be, I think, Boulder and Longmont. We've all used maps like that. But now let's draw a different map. That's this one over here. Let's have time. Well, first of all, this is a static map. It doesn't have time. If you wanted to show motion, you could have a stack of those on cards, and perhaps you start in Boulder driving to Longmont, so you'd be there, and then the next slice you might be there, and so forth. You work your way up. But we can do something on a single drawing like this. Here's time going up, and here's the distance between Boulder and Longmont this way. So if you don't move, if you just are in Boulder and you don't move, you have a trajectory on this map because time is advancing. And that arrow represents your motion on this map. If you were in Niwot and don't move, you have that trajectory. If you're in Longmont, same thing. But if you move from Boulder to Longmont, you would have a trajectory that's tilted over like this, right? You start in, whoa. I know what happened here. I advanced the, sorry, go over here. So on this type of map, you would start in Boulder, and as time advances, you would eventually find yourself in Longmont. Okay? You would be going slow, because it took you an entire week to go 30 miles, walking slowly. All right. Now we're going to do something more with this. We're going to pick the right units. Let's look at this for a second. So what we all agree is that the distance Boulder to Longmont's maybe 20 miles, and that's 5 days. The slope of this line tells you your velocity. Now let's change the units because of the topic of our lectures. Let's change the units so that distance is not in miles, but is in light seconds. And time is in seconds. This is done because we want to show the trajectory of a beam of light. There's a car, we're moving very slowly. You can see the car on this scale does not move many light seconds in a second. A light second is 186,000 miles. So a car is not advancing very far. A rocket ship does better. Notice that the slope has tilted. Light rays propagate at a 45-degree angle. Okay? Because in 1 second, light travels 1 light second. So this kind of map gives us a graphical way to talk about some of the things related to the topic of inflation in the universe. This is excluded. A slope like this implies that whatever's moving that way is moving through space faster than the speed of light. So this is not allowed. Remember, the restriction that Einstein provided was objects cannot move through space faster than the speed of light. To repeat what I said earlier in this lecture, space can expand so that objects are moving away from each other faster than the speed of light, so long as they individually are not moving through space faster than the speed of light. So if the expansion of the universe is fast enough, a distant object can be receding from you faster than the speed of light because space is expanding. Okay, so now let's talk about our experience. Time is going up. That distance we're measuring horizontally. We're just showing one dimension of distance. This is where we are right now. Each of us is right at that point. Now, of course, that point is moving because time never stops moving. Everything that has happened in your life, in fact, everything that's happened in the life aggregate for everyone in this room is in this cone back here. Because nothing faster than the speed of light could have happened in our past. Everything that happened back here gets us to this point. So we live in this cone. It's called a light cone. Our entire future is confined to this cone. Because nothing we do can get us going faster than the speed of light. Starting at this point, we can never get out of that cone. We can do 2 dimensions. This is a little fancier, right? You can see if we were willing to confine our life to 2 dimensions, there are the 2 dimensions, time's still going up. That's as much as we can do on a flat piece of paper or a video screen. So we are here, and everything that happens in front of us inside that cone. Yes, sir?
How do we get to the left side of the cone? Because time is going
up.
And
When you say left side of the cone, do you mean here?
Yes, how do we...
Oh, okay.
How would that happen?
Easy. So here we are at Fort Collins. The time is going this way. If we went south, back toward Boulder, and we placed, remember this is position. So put Boulder here and put Cheyenne, Wyoming there.
Oh, okay.
Everybody follow that?
Yeah, no.
This is Fort Collins. Boulder there, Cheyenne there. If you want to head in the direction of Boulder, go south, your trajectory would be in here. If you want to go north to Cheyenne, you'd be in this part. Okay? Oh, yes. So, here's the same 2-dimensional light cone. Things that happen outside of the cone can get to us because this point here, let's say a star exploded there, that can enter our light cone. We could intersect with stuff that happened over here. We can't go to the place and time where that happened. That would require going this way, which is not allowed. But things that happen outside of our light cone can find their way in. We can never go to these places. Let's say it another way. Any of these dots can send us a signal, a light beam. So now we have some skills with this. Now let us take 2 cameras designed to see microwaves. They don't see stars, they don't see galaxies, but they see this strange glow from the early universe, and we point them in opposite directions. So we're getting light from one of them, camera A is getting light from north of us, and camera B from south of us. We've removed all the starlight, so we're actually looking at the cosmic microwave background left over from right after the Big Bang. Looking north, we would get that measurement, and looking south, we would get that measurement. So here's the dilemma. When we do that, we discover that the variation in temperature on the sky, looking 2 opposite directions, is measured in a scale of 1 part in 100,000. Why? How can it be that the universe is that uniform in temperature unless these 2 points were together when the universe was born? Because things that are together can come to thermal equilibrium. If you put a piece of ice next to a fire, they will come to thermal equilibrium. But if they're separated, they won't. And in this case, we're talking about 2 points. If I look that way and that way, those points are billions of light years apart. How can they be at the same temperature? How could they have been in thermal contact so that they're the same temperature to 1 part in 100,000? That's a mystery. So I just said these things, and this is the illustration. If you have a thermometer and a piece of copper, it takes a while for the heat to find its way from the source of the heat to warm up the thermometer. And in the case we're talking about, billions of light years apart. Yes, sir?
Earth's atmosphere doesn't affect temperature.
Earth's atmosphere only was an issue the first time this was measured was from the ground. And we were looking through the atmosphere. There was some effect. All subsequent measurements are made in space. So this is a dilemma. And here's how to depict this dilemma. Here we are at Fort Collins now. Everything we experience must have come from this cone. Remember, we agree our entire experience has to have come from inside this cone. And our measurement of A, this light was became available to us after the universe was aged 380,000 years. So this light's been around essentially forever. So this point and this point must have been in contact when the background radiation was produced. Otherwise, they couldn't be at the same temperature. And yet, they are at the same temperature. We measure them, and they're the same to 1 part in 100,000. That's the dilemma. Monopoles, I already explained, this is a theoretical particle we should be seeing if our standard model of subatomic particles is correct, and it seems to be really good. Where are the monopoles? And flatness. Now let's talk about flatness. Let me see if I have a cartoon here. I do not. Okay, flatness. Imagine the universe started out lumpy, like a raisin. A big raisin, but a raisin. Now, when we look at the universe, it's really, really, really flat. Remember last time we talked about the geometry's definition of flatness. The universe is extremely flat. How is it that this lumpy thing became flat? So we have 3 problems. We have this horizon problem, we have the temperature problem, we have the monopole problem. There's the first problem. Long ago in the past, the inflation model says long ago in the past, every part of the universe must have been in thermal equilibrium and then somehow got as big as it is now. But since the 2 thermometers matched back then, they would still match now. That could explain why when we look at the sky, we see the same temperature to 1 part in 100,000. Flatness problem. The early universe was lumpy, but because it grew in size so rapidly to become the size it is now, if you take a raisin and inject a little connector to it and inflate it to something the size of our planet, it's going to be flat. All the wrinkles will be stretched out. So the flatness problem is explained by rapid inflation. We still get to the size the universe is today, but in the process we stretch out all the bumpiness and we get something that's extremely flat. And we'll talk about flatness more. Oh, and the monopole problem. The early universe may have had an abundance of monopoles, but if the universe had this explosive inflation in its early days, the monopoles that existed in the early universe and are not produced in any other mechanism we know about, they'd be dispersed over a very large universe. A universe bigger than the one we can see, because the size of our universe is about 45 billion light years in size. So all those monopoles will be stretched out, and there might be one in our galaxy, and we'll just never see it. It might be there, but we would never see it. So this inflation model, which has proved to be very successful, is a foundation of modern cosmology. We'll talk about it more. So we have a few minutes. I want to show you pictures from the accelerator facility in France/Switzerland. This is based on the trip Judith and I took there in 2012. There we are, with our hard hats on. It's an enormous facility. I don't know if you can see this, but there's a railing and stuff there. Everywhere we went, we were guided by a nuclear scientist. And they said the following things over and over again. If there's an accident, we climb those stairs. If there's an explosion, we climb those stairs. If there's a magnetic field incident, we climb the stairs. The stairs, 100 meters up to the surface. And my wife and I were younger at the time, but there was no way we were climbing 100 meters of stairs. So here's what they do at CERN. They have, I'll show you how they do it. But they are able to go back to a point when the universe was about this temperature. This represents what was going on in the universe billionths of a second after the universe started. In that interval I talked about where atoms couldn't exist. And they do this by colliding beams of protons head on. They have a beam going this way, they have a beam going that way, and it's like what's the car race where you crash the cars on purpose? Demolition derby. Thank you. They are demolishing protons by getting them to hit head on, and they produce this, a quark gluon plasma. Remember we talked for a few minutes about quarks. I also mentioned gluons, which is another part of the model, some kind of particle model, and they have this accelerator. It's 27 kilometers around the track. And they guide the protons so they crash into each other. This is a picture of one of the sensors where the collisions occur here, and all the rest of this measures what happened. There's a human to give you a sense of scale. It's a gigantic facility. It's right outside Geneva. You can go. We were lucky enough to get actually a tour below ground. So just for orientation, here's the airport in Geneva. The CERN facility is right there. It's, as I say, it's below ground. They picked a spot where the geology is stable, so they have a nice seismic-free place to build this ring. There are actually multiple rings down there, and it sits right on top of Geneva like this. So what they do is they have a proton source here, and they accelerate protons to some energy, and through a bunch of unbelievable complexity, they get it into this proton storage ring. And they bring it up, they bring the protons up in energy until they're ready to go on the big ring, which is this one. This is called the Large Hadron Collider, LHC. They're currently shut down and are increasing the energy and the performance of the sensors. In the process of doing this, they produce a beam of neutrinos, those invisibly small particles, and those go to in this direction to a place called Gran Sasso in Italy, where there's a neutrino research facility. They do not have to dig a tunnel, because neutrinos don't interact with normal matter almost at all. Interactions that occur are extremely rare. Right now, billions of neutrinos are going through each of us, and they're not interacting with us at all. In your life tonight, no neutrino is going to interact with anything in your body. But if you do the right things, you have a strong neutron source, like they do at the CERN. They can get a beam at Gran Sasso and do research on the properties of neutrinos. When two protons collide in the tube, by the way, the beam is running in a tube this big. And the protons, which are charged particles, can be guided by electromagnets. They have an enormous amount of electromagnet technology. When collisions occur, they get a debris like you would get if you smashed your watch with a hammer. You get all the parts flying out. And some of the parts go over here, and some of them produce this cloud, which is detected and taken care of. Here's an example of one of the magnets. That's the top of the magnet, that's the bottom. Those are normal size units. And the beam, when it's running, would be right in here. When you go down in the ground, it's like going into a space station. Notice, danger, magnetic field, radiation, high voltage, areas where there's no oxygen, low temperature. Here's the control room for one of the experiments. I should point out to you, when they do these experiments, like look for the Higgs boson, they have multiple experiments around the rig. And they say to the team over here, you guys are looking for the Higgs boson. Don't talk to anybody. These people are here in this experiment, they're looking for Higgs. They don't talk to anybody, except themselves. And when both teams are ready to report results, they have two independent measurements, because they have two independent teams using different technology. So they can't be confident they've done this right unless they have independence. The day we were there, they were having a crisis. There's a quote here about how long it takes. If you shut down the beam to do work on the beam, you better have a good reason, because once the beam is shut down, everything in the facility warms up. All the low temperature magnets warm up, and to get the thing back running again takes weeks. Like it says up there, it's like going to the moon. Once you turn it off, it takes a while to turn it back on. The day we were there, this group of people, you could see these two guys are not happy. Imagine the control room is here. The tour guide was over here talking to my wife, and I did this. I stood with my back like this, and I had my camera, and I was taking pictures, because these guys were in a panic, because the beam was running, and it's extremely expensive. It takes a huge amount of electric power. The beam was running, but their experiment wasn't on. And they were furious that the beam had started, because they couldn't turn on their experiment while the beam was running. So you get this dramatic picture of one of the magnets. And I have to say this, April of 2012, we were at CERN. July 2012, Higgs boson was announced. Coincidence? I don't think so. Here's a joke. Neutron walks in the bar, with a beer. How much will that be? No charge. If you don't see the humor in that, you have to talk to one of your neighbors. Okay, we're out of time unless you have questions. I'm happy to stay for a while and answer questions, as long as you weren't here, so I will tell you one of the ground rules. If you ask me a question that the whole class should know about, I may ask you to just hold the question, but go ahead and ask your question.
How is the heat managed if they can produce that much heat? How is that dispersed or
Remember,
managed?
this is a collision of two protons in an invisibly tiny space. The total amount of heat produced in a collision, I mean, you wouldn't want to put your hand in there, but the technology in that area where the collisions occur is designed to carry away the heat. And in fact, they don't just carry it away, they measure it. They're very important. They have a thing called a calorimeter. I'll show you the calorimeter in a second. Right over here. This is a calorimeter. It tells them the heat flux from the collisions. But it's not something that would like start a fire. Now it is true, in 2008 they had a failure of one of the magnets and an explosion. And that shut down the facility until like 2011. We were very fortunate when we were there. The experiments were underway because they were hot on the trail of the Higgs boson. Okay, other questions? Yes, sir.
If the accelerator in Texas were to have been built, what are the energy levels that it would achieve?
There, this is the superconducting super collider that was proposed in the kind of like 1990s.
Reagan, 80s.
Yeah, right. And where Congress killed it.
Well, they started.
Yeah, they did some earthwork and concrete work. the superconducting super collider would have gotten into like the 30 teravolt region. CERN, I think right now is upgrading, and they'll be at 27.
Oh,